Section 1.5 deals with resonance, and this is going to be one of our 5 major areas that we're going to talk about: acid-base, resonance, electronegativity, polarity, aromaticity, and sterics. So this is one of the really important and vitally important keys to understanding and being able to explain organic chemistry. So at the beginning, many molecules and ions can't be fully represented by a single Lewis structure. So we've just finished drawing some Lewis structures. We're going to be drawing sets of Lewis structures that are going to be representations of the same molecule. So 2 Lewis structures that have the same placement of atoms. None of the single bonds change, so the atoms are all attached in the same places, but they differ in the arrangement of other electrons, are going to be called resonance structures. So for example, I can take this amide anion, and this is a specialized arrow. So this is a resonance arrow. It has a single line with a double head. That's different than this kind of arrow that has a half arrow in one direction, half arrow in another direction. That's an equilibrium arrow. So we have a few specialized arrows in organic chemistry. So anyhow, this is a resonance arrow. So if instead of having this lone pair here, I make that into a bond pair between the carbon and the nitrogen, so there's a double bond there, I would have too many bonds to carbon, so I have to push another electron pair of this out onto the oxygen. Oxygen already has 2 lone pairs, so as I push ones out onto there, it's going to change the oxygen charge. So if I look at that structure, here my nitrogen had 2, 4, 5, 6 electrons that belong to nitrogen. Nitrogen only has 5 valence electrons, so that's why this nitrogen has a negative charge. Here, this nitrogen has 2, 3, 4, 5 electrons that belong to it, so that's now neutral. However, this oxygen now has 2, 4, 6, 7 electrons that belong to it. Oxygen has 6 valence electrons, so this oxygen now has the -1 charge. These 2 structures all have the same placement of atoms. If you look, HCO, then NH, HCO, then NH. So the same placement of atoms, the difference is where the electrons are, and you can see that that also changes where the charge is. On this one the charge is on nitrogen, on this one the charge is on oxygen. You might want to ask, which one of these is the correct structure? And the answer is really neither. The true structure, I'll put that in quotes, the true structure is a hybrid of both of these. Don't confuse that with hybrid orbitals. We'll talk about hybrid orbitals more in a little while. The true structure is a hybrid of both of these structures. And so if we're going to try and draw the hybrid structure, what we'd say is every bond that is sometimes single and sometimes double, we draw as a dashed line. So there's always a bond here from nitrogen, and there's always a bond here to oxygen, but there's a dashed line bond here in each of those places because those are sometimes double bonds, and we would say that there's a partial negative charge, that's a delta, on oxygen and a partial negative charge on nitrogen. That's the hybrid structure. And what makes this better? Why does resonance happen? Hopefully you guessed it because you heard me say the word why. It's going to be lower energy. And the reason that it's lower energy is that the electrons are delocalized. So rather than have the charge all localized here on nitrogen and having all the charge there, or all the charge localized here on oxygen, that charge is spread across the oxygen and the nitrogen both. And so rather than having all that electron density in one place, it's spread across a larger part of the molecule. And that causes lower energy. So anytime that we have delocalization, of charge or of electrons is going to be lower energy. And then when we have this kind of delocalization due to resonance, what we can say is that that molecule or ion is resonance stabilized. Now, one of the things that I didn't do up here that we can do is we can also start using our arrows to show electron movement. So if I take an arrow from where these electrons started to where they end up, okay, that takes this pair of electrons to form the new double bond, and I take an arrow and take this pair of electrons out onto oxygen. I can show electron movement with arrows. So curved arrows show electron movement. And that's going to become really important as we start drawing more mechanisms, because a mechanism has to show curved arrows and show electron movement, otherwise it's not a mechanism. Now these resonance structures are not isomers. We just finished talking about isomers. They're not isomers because they don't differ in the connectivity of atoms. Now we want to know, how do you determine which resonance structures are better? So there's a lot of different resonance structures that can be drawn for different molecules. Some of them are better than others. So I'll give you 3 basic rules to look at. 1, more bonds. Structures that you can draw more bonds in are better than ones with fewer bonds. Fewer charges. So if you can draw an uncharged molecule, that's a better resonance structure than one that has a charge separation with a positive and a negative. And the third one is having a negative charge on a more electronegative atom. Which gets at another one of our areas of the importance of electronegativity and polarity. So when we have better resonance structures, they're called major contributors to the overall hybrid structure. And if we have worse resonance structures, then they're minor contributors. And hopefully that makes sense. So if the better the resonance structure is, the more of that resonance hybrid that's going to be in the form of that better resonance structure. So let's look at an example. Keep this simple. I'll look at formaldehyde. So in formaldehyde, I can draw it with a carbon-oxygen double bond, or I can draw a resonance form that pushes this pair of electrons out onto oxygen. Now remember, there are already 2 lone pairs on oxygen, which give it a total of 6 electrons, which makes it neutral. And once I move those electrons out onto oxygen, now 3 lone pairs on oxygen, so there are 7 electrons on oxygen. So this oxygen now has a -1 charge. This carbon now only has 3 electrons that belong to this carbon, so this carbon has a +1 charge. Okay, so pause the video and look at the 2 resonance structures and determine which one's the major contributor and which one's a minor contributor. So hopefully you can figure out that the first one is the major contributor and the second one is the minor contributor. But let's look at why. So first of all, our first rule, more bonds makes a better resonance structure. So in the first molecule, I've got 1, 2, 3, 4 bonds. In the second structure, I have 1, 2, 3 bonds. So that makes this one better. Second, fewer charges. This one has 0 charges. This one has a plus and a minus, has 2 charges. So again, this one is better. So that's why this is the major contributor, the neutral version, and this is the minor contributor. We'll see reactions later on when we get into carbonyls about why, even though this is a minor contributor, it's still an important resonance structure.